afternoon, Professor.
Yes.
Good afternoon, Professor.
Oh my God. Yes. I mean, hi. What? Hi. Hello, Savannah. Hello, Caroline. That was, oh, and here we, it shouldn't make me so happy, but it really does. And I'm not trying to be competitive, but if there were a competition, you'd win. And hello, Amanda. Okay, wait, I'm seeing the chat, but thank you guys. That just makes me, especially because I haven't seen you. So, okay. Hello. So that was Savannah. Yes. Good afternoon, Amanda. Hi, Christina. Sorry, wait, I'm letting more people in. Really, I really should calm down, but no. Oh, and you guys were even, can I just point out, and this is not about anybody who didn't just say hello, this is just whatever. Like, but those people that just said hello, it's like not even 12:15. It's, or I mean, it wasn't, it was 12:14. Not that we're, anyway, all right, whatever. Hold on. So, good afternoon, Amanda. Hi, Christina. Good afternoon, John. Good afternoon, Kevin. Good afternoon, Caitlin. Good afternoon, Amy. With more people come. It's also a good, then I don't have to ask, is the audio working? Like it's clear that it is. Okay. Good afternoon, Amy. Good afternoon, Sophia. Good afternoon, David P. Good afternoon, Felicia M. Good afternoon, Alicia. Sorry. Good afternoon, Kimberly. Good afternoon, Chloe. Awesome. Oh, good afternoon, Nicholas. Yes. Okay. Wait. Sorry. Also, wait. So, and I said yes, and specifically Caroline, Amanda, and Caitlin. Great to see you. Savannah. Great to see you. And I mean, and great to see everybody. But I'm seeing that it's more okay. Anyway, everybody's a winner, but some people are winning twice. What? Okay. No, it's great to see you all. I was going to say, I feel what? Wait, more people coming. I mean, I feel like I haven't seen you all forever, and the reason is I haven't seen you all forever. And more people are coming. Okay. We will get rolling the second, and of course, as usual, like I owe you way more. I owe you tons. You don't owe me anything. We're not even, and like we're having class like it feels like once a week. So I just want to stay. I'm in a minute just gonna get to material. Like, don't worry about like, right now if the semester were to end, we wouldn't have had an exam and you'd all get good grades. It's fine. Like, I mean, we will have exams and stuff, but there's nothing, I don't even want to think about an exam right now when we're still just like trying to squeak through 75 minutes of instruction a week. So I'm just going to get back to instruction. I'm going to forgive me and then get back to all the homeworks and all that. Please forgive me. But you're doing fine. I'm not. I mean, I am. Anyway, whatever. So I want to, so hello to the people that just came. Yeah. Like, hello, Adon. Hello, Elda. Hello, Nicholas, if I didn't say, I think I did say. So I want to just go again, right, let me just get to physics. But if there's any concerns or anything, and some people have, please put in the direct chat or text or whatever. But right now we're just trying to like learn physics. I mean, because it's called a physics class. So where I want to go to, in my notes or my memory, we had just finished, last we met, we actually did finish going over homework 4, which is nice. And since then, homework 5 was assigned. Good afternoon, David K. Good to see you. I mean, good to read your greetings. We had just finished homework 4 and we're now like actually turning to homework 5, which means we actually are not behind ourselves, strangely. But I want to quickly, good afternoon, Adon. Great to see you. I want to just quickly remind you of like the very last equation we got. We're going to get a new one today. We should get another one today. I didn't write it yet because sometimes maybe that confuses people. But this equation on the board here is the very last one we got. I may in a moment write you a list of all the equations we have so far. But and we're going to apply this equation and develop a new one as we discuss homework 5. Oh, good. Okay. Oh, it would be helpful. Okay, then I will. Okay, cool. I thought for a minute, I thought she meant, yeah, it would be helpful to go over homework 5. And I was like, well, yeah. Okay, but no, I got you. Okay, I will do that. Let me say one thing. When I give you this, I will turn the page and I'll just give you a list of the equations we have so far. The one thing what I want you to notice, and again, of course, there'll be, as I always sort of say, the rate of equation acquisition per unit time in this class will steadily increase. Like, sure, equations will start coming a little bit faster and a little bit faster, but never as fast as in chemistry, I don't think, or something. Like the weird thing about physics, physics is not actually about memorizing some huge list of equations, although it may seem that way sometimes, or it may feel that way in high school. Physics is not actually about some enormously long list of complicated equations, and it's certainly not about formula. Oh wait, more people coming, sorry. The weirdest thing about physics is that the deeper you go in physics, the farther one goes in physics, the shorter the list of equations becomes. Like, honestly, like the deeper we go in physics, the more we find out that more things that seem unrelated or disconnected are actually all part of one way of thinking. And the actual goal of physics, this is what I personally like about it, the goal of physics ultimately is to be able to explain and analyze and predict as much as possible with as little information as possible. So the truth is, we're not trying to, and that's why sometimes physics feels weird to people. Physics class can feel too weird. It can just feel unusual because we're not actually trying to accumulate a ton of knowledge. We're trying to accumulate very, very like specialized, specific principles or definitions or observations or ways of thinking that crack open the universe and give us the access to all the details on our own. Like, honestly, it's like a way of thinking that then brings all the details to us. That's the hope of physics, or the idea. So we're never going to get as many equations as some of you might maybe expect, but certainly we're going to get more and more. I'll give you the list right now of what we have so far. But I also want to say that when we have an exam, which we will, and if I, you're going to be given a list. This list I'm giving you now, you're going to get on the exam anyway. So you don't want to even be putting, it's good to be keeping track of this, but you don't even want to be straining your brain to try to memorize these equations. What you want to do is see how they make sense, how after a while they would just be in your synapses naturally or organically if you practice the material enough, because in fact, they're not supposed to be formulas. These equations that we have in physics are literally equations. Like, they're ways of saying one way of identifying something is equal to another way of identifying something. They're just recognitions that two seemingly different things are actually not different. They're actually related. So in fact, it sounds like I'm stalling. I'm about to write the list of the equations that we have so far, like as per Savannah's enthusiastic affirmation, and she should submit that for class participation. But I'm about to write the list. But one thing I want you to notice when I write the list is that all of the equations in the list until this very last one that we just most recently got, all of them are triple equal sign, except until this last one. I.e., they're all just literally definitions. They're just like, when we say this, we mean that. And so hopefully they just make sense on that level. They're just mathematic translations or symbolic translations of concepts that we hope are already in our mind as language. Okay, until this last one. So this last one's interesting because this last one is the first equation we get that's only true under certain conditions. That's what we want to flesh out and practice and remind ourselves of today. But here we go, because I think I'm glad that Savannah like sort of echoed that this might be a good idea. So I'm going to just quickly write you right now on the next page, the equations we have so far, sort of as review, since we haven't seen each other in a while. So and people are coming, and I'll change the view. And there's something in the chat, but I think it's hellos, but hang on a second. Oh yeah. Oh, good morning, Samuel. Thank you. And thank you again, Savannah, for that. Good afternoon, Adon. And good afternoon, David. I think I said that. And good afternoon, Nick. Okay. So that was a chat. So here's the equation. So equations. But, and again, notice I never call them formulas. Formulas imply some sort of like recipe that just was like discovered by someone and then we memorize because it seems to work. These are statements of equality that I'm about to give you. Okay. And with each one of these, there's more than one way to write them. I'm writing them one way, you know. Wait, there was one, is there another equation that I feel like I'm missing? That's funny. Maybe not. If you think there's an equation, well, I'm about to write the fifth and eighth, but if you think there's something if there's another equation, oh, I know what it was. Yeah, okay. Oh, well, that was true, but okay. So quick. So as far as I'm concerned, these are the mathematical expressions we have so far in the class. Like these are the symbolic ways of writing all the ideas that we have so far in class. And, you know, I think they're cool ideas. There's like a pattern in these equations. So they're all about like velocity or acceleration, because that's all we're talking about so far. The different rates at which we navigate through space and time. Now, again, if this all seems like a lot of talk about velocity and acceleration, please remember all of physics is about motion through space and time. What we're doing in these early chapters is we're getting down the fundamental meaning of the terms by which we measure motion through space and time. So the first one is, you know, the definition of average velocity, change in position per time. The second one is definition of average acceleration, change in velocity per time. Then the third one acknowledges, oh, wait a minute, if you're going to change your velocity per time, then that must mean that we don't just have a concept of average velocity. Like we start with the concept of average velocity, how far you got per time over some interval of space and time between 2 points, right? Like the first, you might want to make a note on this about this in the margin or on the right-hand side. Like the first two equations are about average measurements made throughout intervals, segments bounded by 2 points in space and time. That's what the first two equations are about. Then the third and fourth equations say, oh, wait a minute. So those are averages between space and time, but apparently things can happen from one point to another in space and time. Like apparently that second equation says, oh, if you change your velocity from one point to another in time, we call that an acceleration. Okay, well, that implies that you could have a velocity at one point that's different from the velocity that you have at another point. So then there's this concept of instantaneous velocity. Like, no, I mean, this again, now I feel like these are all just concepts and whatever, but you know, note we start getting picky about these symbols now. Like in the third equation, all of a sudden we're defining a V that doesn't have a bar over it. So it makes a real difference whether V has a bar over it or not. When it has a bar over it, it means average. That's the first equation. In the third equation, V does not have a bar over it. So there we're talking about the meaning of instantaneous velocity, velocity at a point. And what is that meaning? The meaning of instantaneous velocity is average velocity, displacement over time, in the limit as the time interval gets arbitrarily close to zero, in the limit as the 2 points in time become so close to each other that they are almost, but not quite, one point in time, right? So that's a calculus notion. In other words, what we're really saying here, I should say, for those of you getting hopefully increasingly comfortable with calculus, what we're saying in that third equation is the definition of instantaneous velocity is the derivative of position with respect to time. The average rate of change of position with respect to time taken to the limit as the interval approaches 1 point. Okay, so again, a sidebar, as long as we're doing this review, since we haven't seen each other for a while, side note, those of you who feel like you sort of understand derivatives or slopes of tangent lines or instantaneous rates of change, maybe that helps you understand the concept of instantaneous velocity in physics better. But for those of you who are like, oh, great, calculus, I never actually, I gutted through calculus, but I never really got it or liked it. Again, I'm speaking to you too. Maybe I'm speaking to you even more. For those of you who were not comfortable with calculus, what I'm saying is this physics might help you understand the calculus better. I mean, sidebar of the sidebar, I know the college requires that you take the math before you take the physics. If I was president, it might just as easily go the other way. Okay, my feeling is I don't know which comes first, the chicken or the egg. What I know is if I understand either one, it's because I kept going back and forth between the two in my life. I would do a little calculus, I wouldn't get it, then I would do a little physics and be like, oh, that's what they're talking about in calculus. Oh, okay, and then I go back, and eventually they just feed off each other. So if I understand what a derivative is today, it's really because I picture instantaneous velocity, and that helps me understand what a derivative is. So vice versa. Okay, so don't ever give up on one because you feel like you didn't have the other. Use each one to help the other. Okay, so and I mean that. So the third equation is the definition of instantaneous velocity. It's really saying it's average velocity taken to the limit, i.e., it's the derivative of position with respect to time. Then the fourth equation, which quite frankly, maybe I never even wrote explicitly, but I'm writing it now. If you're seeing the pattern that's going on here, the fourth equation says, okay, so the definition of instantaneous acceleration, like, is average acceleration taken to the limit. In other words, if velocity is the derivative of position with respect to time, then acceleration is the derivative of velocity with respect to time. In other words, it's the second. So I'm writing it. I've never written this before. I'm writing it. Well, maybe I don't know if I have or not, but I'm writing it now. And I'm writing it illegibly. Acceleration is the derivative of velocity, the rate of the instantaneous rate of change. Velocity is the derivative of position with respect to time. So acceleration is the second derivative of position with respect to time. Okay, so far we have we have average rates of change, and then take it to the limit, we have instantaneous rates of change. And it's a pattern. Acceleration is analogous to velocity. It's not the same, but it's analogous. Okay. And just again, notice in the first four equations, all we're doing is defining our terms. Like, we're just explaining to ourselves in symbolic language what we mean by these rates. That's the first four. Then the fifth is another equation about velocity. I start putting arrows over the V's there to emphasize that velocity is a vector quantity. Frankly, to be honest, I could have put arrows over all the V's and all the equations, but it gets confusing and clunky because there's also the bar, so I just don't. But by the time we get to the fifth equation, I'm putting arrows over the V's to emphasize that it's a vector quantity, that it has magnitude and direction. And we're going to expand. We're going to have to look at that more deeply as the course progresses. But then I'm also putting subscripts on the velocity. So by the time we get to the fifth equation here, which is slightly confused, it's the fifth equation in this course, but what might slightly confuse people is that I refer to it always as GPR form number 4. It's the fourth form of the Galilean principle of relativity, of Galileo's, right? The first three forms are in English. This is the first mathematical. So it's the fifth equation in this class. So the numbers to the left are just like how they've appeared in this class. You don't have to, they're not called in life like equation number 5 or something like that. But that one, the VAC equals VAB plus VBC, I do generally, I mean, throughout physics 204, I'll even keep referring to it as GPR, form number 4. It's the fourth form of the principle of relativity. It's the mathematical expression of the idea that so it's like the train of thought equation that we're going to use. It's saying, it's another observation about velocity. It's reminding us that velocity is necessarily always a relation between two objects. It's never just a property of one object. It's a relation between two. So that if we're being careful and rigorous, anytime we ever write a velocity, we actually should always have two subscripts next to it. Sometimes we don't, because frankly, sometimes we're just assuming that we mean velocity of an object relative to Earth or relative to the lab. In fact, let me slow down and say this to you. If ever, in fact, you might want to write this down as long as I'm summarizing all this. If ever we talk about velocity in this class, like whenever we talk about velocity in this class, if ever I don't have two subscripts next to it, that doesn't mean I still believe that velocity is a relation. If I never specify the two subscripts, if I never say velocity of the car relative to blank, yes, that's because I'm assuming if ever anybody doesn't specify the reference frame, they're assuming that the reference frame is what we call the lab reference frame, like wherever your laboratory is that you're doing this experiment. And if we're talking about things in the outside, like cars and rockets or baseballs, then what is the lab? I mean, it might not be room, oh my God, it might not be, the third floor of John Jay. The lab might be planet Earth. And most labs, like such as the one on 3.65 of John Jay, that lab is fixed to Earth, right? Like, so the reference frame of that lab is the same as the reference frame of Earth. They're not the same location, but they're the same reference frame because they're both always moving at the same speed as each other. That lab is fixed to Earth. If the Earth is going 65,000 miles an hour past the sun, so is room 3.65 of John Jay. So in other words, I'm just saying, velocity is always a relation. If ever we forget to specify what it's in relation to, we're assuming we mean the lab or planet Earth. But we're not always assuming that. So anyway, so equation 5 is reminding us that really velocity should always be a relation between two objects, and specifically that the relation, that velocities in this relational manner add up in the manner of vectors, i.e., just to remind you, just because I'm summarizing now because I'm doing this, equation 5 is the thing that says if there is an escalator moving at 10 miles an hour relative to the Columbus Circle subway station mall, right? Like if the escalator is going 10 miles an hour compared to Columbus Circle, and you are walking on the left side of that escalator at 2 miles an hour relative to the escalator, right? Or I'm going up, but it's going down. Like you're going into the subway. You're like late. You're like a New Yorker, right? And you're doing your thing, and you're like annoyed with all the tourists. They're like standing around, whatever. So you're in the left, and you're booking it down the escalator. If you're going at 2 miles an hour relative to the escalator, and the escalator is going 10 miles an hour relative to Columbus Circle, then you are going 12 miles an hour relative to Columbus Circle. And that's why you're running, because you believe that. You believe running will make a difference, but that's also why you're taking an escalator, because you believe the escalator is making a difference. You believe that both those velocities are adding together. And you know in your heart that if you ran up the down escalator, as my 8-year-old still loves to do, and my 19-year-old son used to love to do, if you run up the down escalator, you know that negative signs will be incorporated. And if the escalator going down at 10 miles an hour relative to Columbus Circle, and you literally ran up at 10 miles an hour relative to the escalator, you know that people watching you would see you do like a wild coyote thing, like your arms would be moving and you'd be getting nowhere, right? Because velocities add in that way. They add according to their reference frames. That's what equation 5, and it's always true, even in cockamamie directions. So that's what equation 5 says, just reviewing again. Okay, so those are the first 5 equations. So again, they're all like different aspects of velocity and acceleration. But then equation 6, now to slow down to where we just got to at the end of last class. Equation 6, it has a double equal sign. It's not a definition. It couldn't be, because equation 6 is about average velocity, but we already got the definition of average velocity. up at the top here, like our very first equation was that average velocity means displacement over time. It doesn't mean average of velocities. It means displacement over time. And we all like suffered through the recognition of that when some of us, when we looked at that up the hill, down the hill figure problem and found out that if you go up the hill at 40 miles an hour and you come down that hill at 60 miles an hour and it's the same hill, your average velocity is not 50 miles an hour, right? Because average velocity means displacement per time. However, what this is saying at equation 6 at the bottom that we just learned at the end of last class is, okay, but under certain conditions, we can compute, under certain conditions, arrive at an answer for average velocity by averaging a first and a last velocity. We can sometimes take the very first velocity v0 and the very final velocity v, add them together and divide by 2, i.e. average them, and we'll get the average velocity, the middle velocity. Sometimes the mean velocity is the median velocity, which sometimes is the same as displacement over time, sometimes is the same, double equal sign, but only under certain conditions, okay? And the condition, it says right there, and this is what I want to like now stress, the condition for equation 6 says it right above, IFF, if and only if A equals A naught. What is that, a different equation? Is that a new equation? That's not an equation, that's a condition. I mean, I'm not saying that A always equals A naught. What do I mean by A? I mean instantaneous acceleration. What do I mean by A naught? I mean the very first acceleration, the initial acceleration. When I write A equals A naught, that is a mathematical or symbolic way of saying the value of acceleration is not changing, right? It's not saying velocity is not changing. In fact, if there's an acceleration at all, anything other than the number 0, then there is a change in velocity. See equation 2, see equation 4. If there's an acceleration, that means velocity is changing. But the rate at which velocity is changing might or might not be itself changing. Like if you're sort of catching on to this whole idea of rates of change, if you're seeing that there's a pattern here, if you're seeing that first we developed velocity as the change of position, then we developed acceleration as the change of velocity. We called the first thing the first derivative. We called the second thing the second derivative. We could go on, right? We could keep making up symbols, and people do. We could define a thing called jerk. Yeah, the guy at the front of the room with the big glasses and the beard. No, we could define a thing called jerk, and that would be the change in acceleration. I mean, that actually is what it's called. And we could say that jerk is the third derivative of position with respect to time. And we could define a change in that called whip and say that it's the fourth. We could go on, and that would be true. And we could eventually run out of words and say, oh, that's why mathematicians like math, because they don't have to keep inventing words. They just say like derivative number 4, derivative number 5, derivative number n, whatever, right? For any rate of change you think of, you can then think of infinite more rates of change. The question is, which one of them means what in the actual physical world? Okay, so I'm saying now, if velocity changes, we call that acceleration. Acceleration itself might or might not change. You can have a changing velocity, but a constant acceleration. You can have speeds that change in an unchanging way. When you do, that's called constant acceleration, right? Not constant velocity, constant acceleration. I think of constant acceleration as unchanging change. It's a paradox, but it's not a contradiction. Right? I mean, it's super important. It may, in fact, be the hub of physics in a way, is for us to be looking at unchanging change, things that change in a steady way. We're going to get more than one equation that, and more than one like piece of knowledge that assumes this very important condition. This important condition that comes up in nature a lot. It's actually it comes up so much and it's so important to study. It's the reason that we like nail down these two derivatives at the beginning of physics class, or like we steal them from calculus class, these idea of two derivatives, but we then don't give you a million more equations with a million more names like jerk and whip and stuff. Like they exist, but we don't get into all that because it's so common and so illuminating in nature the case where derivative number 2 exists, but derivative number 3 is 0. This is a very big theme in physics known as constant acceleration. We have a number of equations that we're about to introduce that apply only when acceleration is constant. The first of them is this equation right here that we got last week. This equation says when acceleration is a constant, then and only then you can use that trick that we said wasn't true on the hill and wasn't true in the Little Red Riding problem. But now I'm saying sometimes is true. There's a trick for computing average velocity by averaging velocities. Now, I'm going to turn the page in a moment, but so I think this sort of catches us up to where we are now, sort of. But let me emphasize again. Am I throwing out our first equation? Absolutely not. Our first equation is the one that you should always, if you're in an exam or you're in a jam, or you are Mr. MC rhyming body slam. No, like if you're in an exam or you're like stressed about something and you have to think about average velocity and you suddenly realize, oh my God, we have like at least 2 equations for average velocity. Like which one should I write down or which one is right or whatever. First, always write the first one down because the first one is always right. It's never wrong. It's the definition. That's why we learned it first. It's always right. It's never wrong. It'll always get you points, like as a GDP, as a step number thing. The thing is that sometimes it doesn't end your discussion for you because sometimes you don't have all the information in it. Like sometimes, as you found out on the hill, you don't have a time or a displacement, whatever. So then if you can then move to this second equation sometimes, and this happened in homework 5, sometimes you only have information that will only like be able to be used if you deploy this second equation, but you have to make sure that it's allowed. You have to make sure that acceleration is constant. That's what happened in the second, in some of the problems of homework 5, which I honestly am about to get to. In fact, maybe I should just do that right now. But the overall summary of how we got this equation is we found out, look, as long as acceleration is constant, as long as you're always building up speed in a steady way or losing speed in a steady way, as long as there's a pattern, then we can make use of that pattern. We saw that as it applies to just raw numbers. Like if every hour I'm gaining 10 miles per hour of speed, then the fact is the amount of speed that I have right in the middle of that time, if every hour I'm gaining 10 miles an hour of speed and I do that for 10 hours, then right at the 5th hour, I'm going to have a speed that's right in the middle because the first 5 hours I was gaining speed at the exact same rate as in the last 5 hours. So all the numbers above the middle velocity will be exactly as much above it as all the numbers are below it. That was not English, but so when you're gaining or losing at a steady rate, you can rely on the fact that your average for the whole thing is right there in the middle of the time. And therefore, you can get away with simply taking the very highest and the very lowest, adding them together and dividing by 2. That's what we found out just looking at raw numbers last Wednesday. This only works for constant acceleration. But when there is constant acceleration, which is often the case in nature, it does work. So, all right, so these are our equations so far. Ideally, by the end of this class, I'm going to derive yet another one. But let's practice a little bit by looking at homework 4. I may want to skip. So I'm going to go to homework 4 now. Okay, bear with. I might even, yeah, I think I'm going to do that thing that I did last time. I'm going to switch the screens now. I'm going to put up homework 4 on the screen, and I'm going to just talk through some of the answers until I get to a big thing. Bear with me. Yeah. All right. So now, right. Okay. So now we're looking at, homework 5. Sorry. Oh, and there's something in the chat. Hold on a second. Let me see. Yeah. Sorry. Yes. Thank you, Caroline, for asking. Yes. So I'm about to go over, I keep saying homework 4. You're right. But I mean to say homework 5. Yes. Because I think, as far as I know, we're done actually going, not that you've all gotten it back, and I'm aware of that, but I think we've gone over homework 4 now. Correct me if I'm wrong. So now we're on homework 5. It's the one that's on the screen. And this is, again, you see it's called midpoint velocity. It's trying to emphasize that as long as you have constant acceleration, your average velocity for a whole journey is your midpoint velocity. It's the velocity that happens right in the middle. And therefore, but only if you have constant acceleration. And therefore, you can get it by averaging the two endpoint velocities. Wait, there's something in the chat. Yeah, okay, cool. Thank you, Caroline. And Caroline gets tons of points for contest participation. And if you sing things like this, then you get even more points, especially if you actually can sing. Yes, there should be a Broadway musical about physics. Wouldn't that be awesome? No one would ever go. Okay, but I would. Okay. All right. So I'm going to talk through, and I think this is kind of a drill thing. Definitely stop me if you have any issues. But I think with this, I want to just kind of say the answers to make sure we're all okay and we get the point and the pattern. And then I'm going to go on to the slightly, so stop me if that's not okay. But so question one, midpoint. So a particle starts out from rest, i.e. its initial velocity is 0, but with an acceleration of 4 meters per second. So you could also write that as 4 meters per second squared. We just sometimes write it different ways to whatever, to some people, they're equivalent. Meters per second means meter per second squared. Either one is fine. The particle continues to accelerate at this constant rate for 20 seconds. Okay, so let me say right now, this problem is telling us explicitly, this is a case not only where there is acceleration, but the acceleration is constant. So this is unchanging change. And we're just trying to see what that means here with these drill and chill questions, okay? But this, in other words, this is going to be a case where you could use that last equation. This is constant acceleration example. It could be a car moving forward, whatever. All right, so what's the particle's instantaneous velocity at t equals 0? Well, it says it starts off from rest. So it's instantaneous velocity v equals 0 meters per second. That's the answer to A. I'm just saying it 0. Stop me if you don't like singing. And that person was so polite to Caitlin, as they should have been, because she is focusing right now. The person just, she didn't even know the person just walked by her. Okay, sorry. All right, so V equals 0 is the answer to A. B, what's the instantaneous velocity at t equals 0.5? Okay, I'm going to tell you right now, I think the answer is V equals 2 meters per second. Now, I did that in my head. You have to show work when you're handing these homeworks. You can't just write that down. You do have to show work. That doesn't mean you have to use an equation. I mean, I see that in my head. Maybe you do, maybe you don't. But if I'm using an equation for this, and I might, you tell me in the chat whether I should do this or not. What equation am I using? I'm using the definition of average acceleration. I'm using what was, I guess, equation, I can't even know. I think, wait, I can't tell. I can't tell. I was using equation 3, A bar E triple equal sign V minus V naught over T. And I rearranged it in my head. And you would do it on paper. I'm saying, okay, I'm looking for V. I'm looking for instantaneous velocity. So I'm solving that equation for V. So I multiply both sides by A and I say V minus V naught equals A times T. Then I add V naught to both sides. So I say V equals AT plus V naught, right? That's just a rearrangement of the definition of acceleration. And again, this is what I would do if I were you, like handing in homework or on an exam. I mean, you could also explain this in English. If you see it in your head, you don't have to force it into an equation. You could tell me in English, but you still have to explain somehow how you see it. What I'm saying equation right now is, equation-wise, is V equals AT plus V naught. Notice I just rearrange the equation first, then I'm going to plug in numbers. Good, important habit in physics. Do all the algebra and everything first, put in numbers at the very last minute. That way, if perhaps you have a number wrong here or there, or a number came from a prior question, or you do something wrong on your calculator, you're going to lose as few points as possible. All your physics is still going to be right. And plus, you're going to be practicing good physics for all the other questions. So I'm saying so far, if you're with me, V equals AT plus V naught. Then I'm saying, well, V naught is 0. Like I was just told that, and I just said that in part A. So V equals AT. What's A? 4 meters per second squared. What's T? A half a second. Right. So I'm doing 4 meters per second squared times a half, or divided by 2. So the seconds cancel out and I get 2 meters per second. That's the answer for B. Now, again, let me just say before I go on, many of you may have totally done that in your head, and Quark plus America if you did. I'm not saying that you need to make it more complicated, but whatever you did in your head, I want you to explain. Number two, if you didn't see it in your head, then hopefully what I just said helped a little bit. Number three, what the real purpose of that question B is just trying to test in a way that we understand what we mean by acceleration, but specifically, it's trying to make sure that we understand a constant acceleration is just that. It's constant. Even if it's a rate of 4 meters per second every second, that doesn't mean that we have to wait a full second for something to happen. It means it's rolling all the time. So if you've gained 4 by the end of a full second, you would have gained 2 by halfway through that second, and you would gain 1 a quarter of the way through that second. It's continuous all the time. That's what these rates mean. Okay, stop me if there's any questions. I'm kind of assuming maybe there aren't, but definitely, even if I'm talking fast, it does not mean you shouldn't stop me. It means I don't want to bore you if you're not stopping me. All right, so the answer to A was 0 meters per second, V equals 0 meters per second. The answer to B is V equals 2 meters per second. The answer to C is V equals 4 meters per second. Exactly the same work as in part B. Like it's the pattern. It's the equation. So D, V equals 3 meters. Oh, sorry, just kidding. Is 6 meters per second, right? I mean, same math, same idea. Stop me if I'm not making sense. Answer to E, V equals 8 meters per second. We're just trying to see the pattern. We're just trying to see what we mean by constant acceleration here. This is a whole exercise in constant acceleration. Notice again, please notice, constant acceleration does not mean constant velocity. The velocities are totally changing, but in a constant way. Okay, F, so now we're like leaping. If you see the pattern, you can extrapolate, or you could make a graph, or you could just plug straight into the equation. What's the instantaneous velocity at 10 seconds? I think it's 40. V equals 40 meters per second, right? What's the instantaneous velocity at 20? V equals 80 meters per second. I'm just saying V equals AT plus 0. Okay. So then we draw, so again, stop me. Oh, okay, I'm totally boring people. Okay. So stop. Then H, draw a neat, careful scale graph. Okay. People hate doing graphs. Most people hate doing graphs. But they turn out to be super important. I hated, just like everything else in all of this, believe me, I hated them until I loved them. How did I pass from hating graphs to loving graphs? The day I realized that unless it's literally in a lab, like in a lab, you make graphs from data points. Like you get in, you make measurements, tons of them, because you're literally doing an experiment. You make tons of measurements, then you take all the measurements, you put them on a scatter plot. Now you have a graph. Now you do things with it. Okay, that's experimentally how you acquire data. But in a theoretical exercise like this in homework, when we ask for graphs, what we want is your axes to be labeled. Absolutely, your axes have to be labeled. Otherwise, the graph, we don't know what it's saying. You have to label your axes, and maybe you want to label like 1 or 2 key points just to see the scale of your axes. So maybe you label a point or 2 or a value or 2. But other than that, what we want to see is axes and then the shape of the graph. The whole purpose of graphs ultimately is to show a pattern or shape or a trend. We really want to know, is it straight? Is it not straight? Is it parabolic? Is it upside down parabolic? Is it straight or curved? And if it's curved, how curvy? That's what we're really looking for. Honestly, you must label, like if this were an exam, I would take off points if your axes weren't labeled. And some of you would be very upset about that because it seems picky. No, without the label of the axis, I have no idea what the graph is saying. But once you label the axis, a rough sketch is what we're looking for. So this graph here in H, what I'm looking for is time on the x-axis, velocity as an instantaneous v. On the y-axis, it's seconds are the units for this axis, meters per second are the units for this axis. And what I would see is a straight line that begins at 0, 0, right? Because at t equals 0, v equals 0. I would see a straight line whose y-intercept is 0 and whose slope is 4, right? For every 1 second over on the x-axis, it goes up 4 units of velocity of meters per second on the y-axis, right? So basically, you just give me a straight line that intersects the origin and maybe label the point 1, 4, and that's it. That's the graph, right? And the key important thing here is the velocity time graph is a straight line if acceleration is constant, because acceleration is the slope, is the derivative of velocity. Now, that's a concept. I'm hoping that most of you get it. If you did the homework, you probably get it. But that's where if anybody wants to have me repeat that or wants to ask anything in the private chat, you should not be ashamed of yourself. Like I'm saying, acceleration is the derivative of velocity. That means acceleration is the slope of velocity. That means if velocity is changing in a constant way, the slope of the velocity graph should be constant. Last thing, if we were to draw the position graph for this, I don't think that would be a straight line. Like this is also why the labels of the axes really matter. It's a straight line graph if we're graphing velocity as a function of time, or for whatever. Okay, now then we get to, but please stop me. It's 1 o'clock. Okay, we're actually making some tracks here. Please stop me if whatever. Now we get to I and J. Now I'm going to tell you right now. I mean, hopefully you're solid with all of this, but again, like I'm cheering those of you who are bored or like nailed all this, like yay, like Quark, bless you. And also, if you did nail all this when you did it weeks ago, or if you're following what I'm saying, please do praise yourself quietly. Like if you're on video, you can turn off for a second so you can pat yourself on the shoulder, whatever. Like if you're getting all this right, what I want to say is don't say to yourself, well, duh, this is easy. Like, duh, like obviously, no. It might now seem easy because you got it right. Nothing is easy until it's easy. And then everything is easy in retrospect. So if you did get this right, you get something important, honestly. If you didn't get it right, don't be ashamed of yourself just because I'm talking quickly. Because now we're going to get to I and J, where I'm going to tell you right now, at least 2 people emailed me. I mean, at least 2 people actually emailed me about I and J, and God knows how many people didn't, had a difficulty and didn't email me. So there's no shame in having a momentary pause on I and J. I and J, or I think it was I and J, I'm pretty sure. Yeah, like I says, what's the average velocity during the first 2 seconds of the trip? Okay, now at least one person, and I'm praising this person, and this person, like I'm not going to name names, but at least one person emailed me about this, and that person should submit for class participation. There's at least 2 portals that they can get class participation for having done that. It was not a stupid question that they asked me. I'm going to repeat it now, and it might even help some of you who might even nonetheless have gotten this right. The person emailed me on I. They said, okay, like what? Okay, so I want to do average velocity. It's asking average velocity, but I don't know the displacement. Like, and they even said, or they implied, like, all right, it's asking the first 2 seconds of the trip. So I know the time is 2 seconds, and they're correct, but I don't know the displacement. And like, don't I need the displacement for that first equation? Now, here's why I'm so glad that they emailed me. They're right on every count. Like, they do know the time, and they are right that average velocity is displacement over time. And they're right that that should be your first instinct. If this were an exam, that is the first thing you should write down. Average velocity equals displacement over time. And it's correct. It's not wrong. It's just that then you stare at it and you're like, I don't have the displacement. Now, with at least one problem we've seen before, it turns out that the fact that we didn't have the displacement ended up not being a problem. We guessed it, we worked around it, maybe we could have found it out, so in other words, it wasn't a misprint, there was things we had to do. So the person was very right to email and be like, okay, clearly this is one, I got to do something now, but I don't know what to do. Now I'm going to tell you in this case, the displacement does matter. It's not like the Hale figure problem where you get the same answer no matter what. That's true. And it is also true that we don't know the displacement offhand. It's also true that if we think hard enough about all these numbers, as we're going to like later on in the sheet, in the next problem, if we think hard enough, yes, we have enough information here that we could figure out the displacement. We could. And that's what I'm going to show you next. And therefore, we could get the answer that way. But it's also true that this acceleration is constant. So this is a case where we have another equation that we could use now, or another concept that we could use, that this problem is trying to get you to practice now. That person who emailed me was totally right in first thinking that average velocity is displacement over time. If they could get all the information, that would work. That would get the same answer as what I'm about to say. But it's also true that the acceleration is constant. So average velocity is middle velocity here. So, so maybe I think I might switch my, bear with, I'm not going to switch the screen yet. I will switch the screen, but I'm just going to say this in English. We have an equation now that says V bar double equal sign V naught plus V over 2. That sometimes the average velocity for some interval is the average of the two endpoint velocities. It is true as long as acceleration is constant. Excuse me. Acceleration is constant in this case. So what I can do here, it just asked me to practice this new idea. I can say, you know what, in the first 2 seconds of that trip, oh yeah, and the hints, problem 6 above. Yeah, the hints are saying what I'm saying now. In the first 2 seconds of that trip, there's a steady change in velocity per time. The very first velocity of those first 2 seconds is 0, like that was our answer to A. The last velocity for those first 2 seconds is answer E, is the answer to question E, which was 8 meters per second, right? So our endpoint, so V naught was 0, V final was 8. So we literally add them together and divide by 2. We add the two numbers together and divide by 2. We average them and we get the middle velocity. The average velocity is 4. And that is the answer to I. The average velocity for the first 2 seconds of the trip is 4 meters per second. Please notice also, not a coincidence, 4 meters per second is exactly the instantaneous velocity that we found in part C to be the instantaneous velocity at t equals 1. In other words, right in the middle of those 2 seconds, we're going 4. This is a pattern. It's not obvious. It's just true. Or of course it is obvious once you see it, but it's not obvious until you see it. So those of you who don't get it or didn't get it the first time, don't beat yourselves up. And those of you who do get it, don't also do the reverse beating it. Don't be like, well, duh. It's not a duh, like until it is. I'm saying now, from now on, from all time, when velocities change in a steady way, when acceleration is constant, then the average velocity is the middle velocity. It is the velocity that occurs right in the middle of the time. In this case, we had 2 seconds. The velocity average for the 2 second interval was the same as the instantaneous velocity right at t equals 1. I'm going to say one more thing about this because this equation is super important. And it's our first kind of this equation says more than it looks like it says as an equation, like V bar equals V naught plus V over 2. If you're taking notes, which is great, and by the way, you can always submit a screenshot of your notes as class participation as well. Like, even though I'm writing things down, I'm not right now, so it's really good if you are. I'm saying that V bar equals V naught plus V over 2. You might even want to put like next to it, like an asterisk or something. What it's saying is V bar equals V bar double equal sign V at t equals 1/2. I'll say that again. V bar double equal sign V at t equals 1/2. If and only if acceleration is a constant. What I'm saying, and then I'll move on. But like, this is where physics starts to get subtle. I started the semester by saying, don't confuse average velocity with average of the velocities. Doesn't mean the same thing. Then I also said in this semester, don't confuse average velocity with instantaneous velocity. They don't mean the same thing. And they don't. That's triple equal sign kind of knowledge. But now I'm saying, okay, but there are conditions where they turn out to be the same. Average, how fast you're going on average is not the same at all in meaning as how fast you're going at a moment. But I am saying now, when your acceleration is constant, then however you're going fast on average is exactly how fast you're going at one special moment, the middle moment. The time equals 1/2 the total time moment. At that moment, the that and only that moment, the rate at which you are going instantaneously at that moment is literally your average for the whole thing. It's like if you're, well, I think you get it, right? But only for that moment. Okay, so the answer for I, I was gonna say, what am I writing about that? There's something about your notes I was gonna say. Well, okay. Anyway, no, what I was gonna say, why that's so important is you're gonna find in physics as we go, the average quantities with bars over them are always easier to find. I mean, to compute, they're easier to solve for and easier to picture. But quantities without bars over them are more precise and ultimately sort of more important. They're harder to picture and harder to compute, but they're more precise and they're more important. So what I've just given you, whether you kind of see it or not, is I've just given you one way that we can convert, in effect, from an average quantity to an instantaneous quantity. What average quantities are the ones that are easy to compute, like displacement divided by time. But we sometimes need to know how fast you're going right now. Well, one trick is, as long as the acceleration is constant, how fast you're going on average is how fast you're going at least exactly one moment, the moment of middle. So that allows us to move back and forth between information that applies to an interval between 2 points versus information that applies at exactly 1 point. It's a very important. So this last, and you can't see all of that by just looking at or memorizing the equation V bar equals V naught plus V over 2. I'm saying that equation is saying a lot of things at the same time. It's saying mean equals median, which also equals midpoint. Anyway, all right, so that's I. Okay, so I'm looking at the time. Okay, so then J, what's the average velocity for the whole 20-second trip? I'm going to do the same trick. I'm going to say for the whole 20-second trip, all right, the initial velocity is 0. The final velocity for the whole 20-second trip was 80. So the average velocity for the whole thing is 0 plus 80 divided by 2, 40. 40 meters per second is how fast you're going on average for that whole trip. And by the way, not coincidentally, that's exactly how fast you're going right at the 10th second at t equals 10, the middle. You see how, and you could see all this on the graph if you made it, or it's meant, or depending on how detailed your graph is, certainly your graph would be consistent with everything I just said. Okay. So anybody who, if you got a lot of that right, but you didn't get I and J right, or you stopped at I and J, guess what? You're getting your money's worth out of this course. Like if you get what I was saying until H, but you didn't know how to do I and J, then that means you're learning something, like truly. I mean, if you get it now. Okay, now, but stop me again. All right, now we go to the next problem here. And I know we have 18 minutes. And hopefully if I do this right, I'm going to generate a final equation for us. And I'll say right now for problem, I'm going to do problem 2 now. Problem 3 looks like pure algebra. It is. It's actually, problem 3. Problem 3 generates yet another equation. So there's 2 more equations someone's in the chat, I'm sorry. But my goal in the next 17 minutes is to show you yet one more constant acceleration equation, an equation that's only true if you assume constant acceleration. So everything we're doing right now is in the context of assuming that there is an acceleration, but it's not changing. And then there'll be yet another equation that we're not going to do today, but that's what the 3 is just trying to show you it's trying to hint at the algebra of how we would get that last equation. Wait, sorry, something's in the chat. Let me see. Sorry. Oh yeah. So Caroline, I thank you for, did I say it wrong? Yeah. I was 4 meters per second. That's correct. And are you asking, did I say something wrong at one point? Or you're just making, please let me, chat again. Oh, and yes, thank you, Felicia. That's multiplayer co-op right there. But so hopefully, can anybody tell me if I said it wrong at one point? I would like to know so I can like loudly correct it for everybody. But yes, that is correct. Okay. So are we okay? All right. So, okay, cool. Okay. All right. So now I'm going to switch boards again. I'm going to go to this next. Well, we have 16 minutes. I'm going to do this second one. Now, the second one's a little confusing. Well, So the second one's called the first second. That's sort of a cutesy name, is sort of confusing itself. But it seems like very straightforward. It's a bicycle. It starts at rest. I mean, it is straightforward, but it's another one of these sort of tricky things. I'm going to tell you right now what the point of the second one is, in a way, to address like the people that sent me cool emails about I and J. Like the second one is now saying, okay, say we know something about the acceleration. Say we have a constant acceleration, and we know the velocity at certain moments. Like, can we now talk about how far an object gets? Like, notice, like nowhere in problem one did we ever actually reference how far the darn thing was going, which is why people wrote me emails, because they're like, wait, how far is it going? So yes, we ultimately want to know that in physics, like how far does something go given an acceleration rate? Question two is now going to get us to see how we do that. And it's going to force us to see that we have to be careful. If you know velocity, you can get displacement straightforwardly. I mean, velocity is defined, average velocity is defined to be displacement per time. Once you know the acceleration, okay, you still can get displacement, but you have to do a couple of steps, because acceleration is not change in position, it's change in velocity. And velocity, in turn, is change in position. So question two is trying to get us to see that we're going to have to do a couple of steps to do things. In other words, I'll tell you right now, since we have now 15 minutes, in question two, a bicycle is at rest. It accelerates at a constant rate of 2 meters per second squared. How far does it travel in the first second? So from 0 to 1 time, I'm going to tell you right now, the answer is not 2. I don't know if you thought it was, or a lot of people think it is. If you think it's 2, don't be ashamed of yourself. Don't drop the course. Don't like cry, but do pay attention. The answer is not 2. That's a common misconception. The answer, actually, I'm going to show you how to get it, of course, but if a bicycle starts at rest and accelerates at a rate of 2 meters per second squared, if we want to know how far it's gone in the first second, the answer is going to be 1 meter. Okay, and I'm going to show you that now, but that's the answer, is 1 meter. I'll even say, if you're looking for a pattern or looking to see, or if the numbers are too coincidental, if this had been the first problem, like the problem above, I guess, is the screen still sharing? Yeah. Like if a particle had accelerated from rest at a rate of 4 meters per second squared, if I want to know how far it got in the first second, I would say the answer is 2 meters. If I want to know how far in the second, I would say 4 meters. If I want to know how far in the third second now, I'm just going to tell you, just so you can see that this is maybe not totally obvious. Looking at that first problem where it accelerates at 4 meters per second squared, if I want to know how far it goes in 3 seconds, I would say 18 meters, which is not obvious at all. It's correct, but it's not obvious. Similarly, I'm going to, in problem 2, if the thing is accelerating at 2 meters per second squared, if I want to know how far it gets in 3 seconds, I'm going to say that the answer actually is 9 meters. Like, where am I getting those numbers? I'm going to show you. Okay, so I have to switch screens, and I know we have 13 minutes. All right. Okay. Okay. So this is now. And again, I'm just, because we only have 12 minutes, I'm not necessarily going through all the 5 steps of like how you'd hand in your homework. I'm just trying to show you. Well, maybe I don't know. I'm trying to show you something. Okay, here, well, here. Okay, so fine. I guess I sort of am. I can, and now you're seeing this is a bicycle, believe it or not. Okay, we have a bicycle. It starts at rest. It has a constant acceleration of 2 meters per second squared, right? And we want to know, and it travels for 1 second. And we want to know, the question is, how far does it go in that 1 second, right? So there's my step 1, the diagram and the facts. Step 2, the question. So now I'm going to, my goal here is to answer this question with the knowledge we have so far, which is sufficient, with the equations, the definitions, the meaning that we have. There's more than one ways to do this. And yes, the goal of this ultimately is to generate a new equation. And maybe you know this new equation from high school or from the interwebs, fine. But make no mistake, I can't assume that you know it and there should be, and I want to show you that that equation actually makes sense. It's not a memorizer. So we should be able to do this without going to Khan Academy or whatever, or back to our high school, right? Like, so with the knowledge we have so far, if this knowledge is at all powerful. So here's what I say. Well, sorry. I say, okay, so I'm looking for displacement, right? Well, I know that average velocity is defined to be displacement per time, right? Oh, and let's even call the very first place where this bicycle starts is like its very first position is 0. Like that's where I put down the ruler, just like the very first time, because there's no reason not to call it that. So I'm looking for displacement. So I know I can rearrange this. I know that displacement equals average velocity per time. I also know, sorry, I didn't mention that. I can now start plugging in. I know that the initial velocity is the initial position is 0. So I know that how far it gets. I know how far it gets will be how fast it's going on average times the time. And I know the time is 1 second. But here's where a lot of people would say, okay, so it's 1 second times 2. So you get 2. So end of story. But 2 is not the average velocity, right? 2 is the acceleration rate. If I want to know how far it goes in the first second, I need to know how fast on average it's going for that first second. On average for that first second, I don't believe it's going 2 meters per second squared. I mean, that's not a velocity, that's an acceleration. What that means is that every second it gains 2 meters per second of velocity. Right at the beginning, it's not going any rate at all, it's going 0. By the end of the first second, it's going 2 meters per second, but that's instantaneously at the end of the first second. So on average for that second, it's no more fair to say that it was going at a rate of 2 than it is to say that it was going at a rate of 0. They're both wrong. One's too low, one's too high. In other words, if I want to know the average velocity for that first second, I don't literally know it. I have to figure it out. Can I figure it out? Yes, I can do this. Because the acceleration is constant, I could say that the average velocity, so I'm using what we just did, in the problem above, I'm saying it went from 0 to 2. Oh, sorry, I should be really clear. I mean, yes, that is what I'm going to do. It's not a mistake, but let me just be really clear. I have to average the velocity right at the beginning, which is 0, that's known, with the velocity at the end of that first second. Now, I'm seeing it in my head, and maybe many of you are, but let me be really explicit. Where do I get that final velocity from? I do the thing that I did before. I go like this. I go definition of acceleration, and I rearrange to get final velocity, just like I did before. Only I spoke it. I didn't write it down before, but right? And I say, okay, the initial velocity was 0. So what I'm doing right here, maybe I'm starting to lose people now. I'm solving for the final instantaneous velocity, the final velocity at the end, right at the end, the last moment of 1 second. Now, again, maybe if you understand that's what I'm solving for, you might just see it in your head. But if the problem were harder, maybe you wouldn't be able to do. So I'm saying, in other words, I'm saying V equals 2 meters per second squared times 1 second, right? So the one of the seconds cancels with 1, and we get that V equals 2 meters per second squared. What is that V? That V is the final V at the end of 1 second. It's not the average velocity. It's been, and this is also what that first problem was trying to show, that these things accelerate continuously, right? So it wasn't going 2 the whole time. It didn't arrive at a velocity of 2 until right at the last moment on average. So therefore, I'm saying, so that's V equals instantaneously 2 at t equals 1. So therefore, the average V equals 0 plus 2, all divided by 2. So the average velocity, here's the key. I'm doing a lot of work to show you something. Again, many of you, some of these steps that people are seeing in their heads. But I'm trying to show you what's really going on, which is that if you want to know how far this bicycle is going in the first second, and what you have is its acceleration rate, you have to be careful and realize that it's accelerating the whole time. So it's not going to the whole time. On average, for that 1 second, it's going 1 meters per second. So now I can plug back in and say, fine, x equals v times t, right? So it equals 1 meter per second for an amount of time of 1 second. So x equals, the seconds cancel, 1 meter. That is the answer, 1 meter. That's how far it goes. How fast it gets up to is 2 meters per second, but that's not how fast on average it's going. So let me do one more, we have 5 minutes. Let me show you, what if we had said, like, just so you see, there is a pattern, but it's not an obvious pattern. Like, what if we had asked at the 3rd second? Okay, at the 3rd second, I'll really quickly show you. At the 3rd second, then I'm going fast now in a way. You see, physics goes a little bit fast. Then v equals at plus v naught. V naught is still 0. So v would equal the rate of acceleration of 2 meters per second squared times 3 seconds. That's 6 meters per second. That would be how fast it's going at the end of the third, right? So it's going 2 meters per second, then 4 meters per second, then 6 meters per second, then 8 meters per second. That's the pattern. The obvious pattern is what the velocities are doing. But that's what it would be doing at the end of 3 seconds. Therefore, if it's going 6 meters per second at the end of 3 seconds, then its average velocity for those 3 seconds would equal 0 plus 6 divided by 2 equals 3 meters per second, right? Its average velocity, if we're doing 3 seconds now, as an example, just to show the concept, if its average velocity is 3 meters per second, but it did that for 3 seconds, then x would be vt would be 3 meters per second times 3 seconds. That's where I got the 9 meters from. And that's correct. And that's right. And it may hopefully make sense once you think about it, but it's not like a number that I would have just guessed, 9. I'm saying if it goes for 3 seconds, how far does it go? It goes 9 meters. And then the next one would be even more than, it'd be like 16 or something. It's going farther and farther each second because it's going faster and faster. What's the summary of all of this? So in sum, and this is the last thing we'll do, we have 3 minutes, but I just want to generate the last equation. If we know A and T and V naught, but we want X, we want how far something's going. If you put together everything we just did, what we just did algebraically is we said this. We said X equals, oh, and this is assuming that A is a constant. We said X equals V plus V naught over 2 average velocity times time. Yeah. And then we said we don't know final velocity. To get final velocity, so I'm just repeating this. This is the last thing we're writing. We said V equals V plus V naught over 2 times time. And we said V equals AT plus V naught. That's what we did to get all this both times, right? So if we substitute that in, what we're saying is X equals AT plus V naught all over 2 times T. That, if you put together the steps that we just did numerically, that's what we're doing. We're putting 2 equations together. We're running 2 equations in sequence. And if you then simplify this, we're saying X equals AT plus 2V naught all over 2 times T. So these 2 cancel, and we're saying X equals, if you distribute the T, we're saying 1/2 AT squared plus V naught T or technically, sorry, if I'm being really technical about this, x minus x naught, x minus x naught, x minus x naught. And this is our final equation. We're ending right here. You might recognize that from high school, you might not. But what x minus x naught displacement equals 1f at squared plus v naught t. You can use it from now on, but it assumes, this assumes that a is a constant. If acceleration is a constant, so this is like the distance equals rate times time statement for situations of constant acceleration. Right? It's saying once you know acceleration, to get displacement is a little bit more complicated than just saying rate times time. But that's that's our last equation. That's equation number, I mean, so far. I think I gave you 6 at the beginning of today. Yeah, I think so. That's equation number 7 for now. And we're stopping. And I actually have to go to a meeting. I'm so sorry, but hopefully that's clear. I mean, I'll post all this. I'll post the video. Just keep doing what you're doing. But I think we're actually, that was, thank you guys very much for being so, oh, great. Oh, great. Oh, cool. Oh, thank you. Oh, what an, oh, that's a million points of class participation and an egg. I don't know why. Thank you, Felicia. No, I hope this could, but there's a lot came from all your questions in the chat and an email, which really helped me know what to tell you. So great. Okay, I'm actually going to go, or I have to go, but I will post everything. And I'm Quark bless America. Oh, great. Thank you. Quark bless America. May the net force be with you. I'm turning off the record.